Module 2. What DNP3 is, Core Architecture and Communication Model. Number 2.1, Purpose-Built Protocol for Utility SCADA and Automation. DNP3 is a domain-specific communication protocol engineered explicitly for supervisory control and data acquisition in utility environments. Unlike general-purpose networking protocols designed for bulk data transfer, DNP3 is optimized for frequent exchange of small, structured data elements representing the physical state of field equipment. Its primary operational goal is to enable reliable, deterministic, and interoperable communication between geographically distributed devices operating over imperfect communication media. DNP3 addresses 4 foundational requirements of utility automation systems: accurate representation of physical process data, deterministic command execution, efficient use of low-bandwidth channels, robust error detection and recovery. Number 2.2, Master Outstation Communication Paradigm. Logical roles in DNP3. DNP3 defines communication roles using functional behavior, not hardware class. Master a system that initiates requests, issues control commands, and maintains a synchronized operational database. Outstation, a remote system that collects field data, executes control operations, and responds to master requests. These roles are logical, not absolute. A single physical device may operate as a master to downstream devices, an outstation to upstream systems, both simultaneously, submaster or data concentrator role. Deterministic request-response model. At its core, DNP3 operates on a request-response transaction model. 1. The master sends a request specifying function code, RAID, control, time sync, etc., data type of interest, object group, variation, and index ranges. 2. The outstation processes the request and returns a structured response containing status information, requested data objects, error or exception indicators if applicable. This explicit request-response structure ensures predictable system behavior, which is critical for operational control environments. 2.3, Data-centric design philosophy. Data as structured objects. DNP3 does not transmit raw memory values or proprietary payloads. All data is transmitted as well-defined objects, each identified by object group number, object variation number, index point number. This approach ensures semantic consistency across vendors and devices. Core data categories. DNP3 natively supports multiple data classes that align with physical utility measurements and controls: binary inputs, two-state indications, analog inputs, measured or calculated quantities, counter inputs, monotonic accumulating values, binary outputs, control points, analog outputs, set points. Each category is formally defined with explicit encoding rules. 2.4, Static data and event data model. Static data. Static data represents the current value of a point at the moment it is reported. Examples include present breaker position, current voltage level, latest accumulated energy count. Static data is typically used for database integrity checks, initial system synchronization, periodic full state refreshes. Event data. Event data represents state changes or significant variations detected by the outstation. Examples include binary state transitions, analog values exceeding configured deadbands, counter rollovers or freezes. Event data may include precise timestamps enabling sequence of events SOE analysis. Event classification. DNP3 organizes events into 3 priority classes: Class 1, Class 2, Class 3. This classification allows masters to prioritize polling and bandwidth allocation based on operational importance rather than raw data volume. 2.5, Polling and unsolicited reporting. Polling-based communication. In traditional operation, the master periodically polls outstations for event data by class, static data at longer intervals. Polling frequency is configurable and reflects trade-offs between data freshness and channel utilization. Unsolicited responses. DNP3 also supports outstation-initiated reporting, where the outstation transmits events without waiting for a master request. This mechanism enables faster event notification, reduced polling overhead, improved responsiveness in large systems. Unsolicited reporting operates within strict protocol controls to avoid message collisions and loss of determinism. And number 2.6, Support for imperfect communication media. Designed for field reality, DNP3 assumes that communication channels may be noisy, intermittent, low bandwidth, high late. As a result, the protocol incorporates robust error detection mechanisms, sequence control for duplicate detection, Fragmentation and reassembly logic, optional confirmation strategies. These features allow reliable operation over serial lines, radio links, leased lines, and IP networks. Number 2.7, transport independence. DNP3 is transport agnostic at the application level. It can operate over serial point-to-point links, multi-drop networks, radio systems, fiber optic networks, TCP IP-based Ethernet, and WANs. When transported over IP networks, DNP3 frames are encapsulated within TCP or UDP without altering the application semantics. 2.8, architectural implications for utility systems. The architectural model defined by DNP3 enables multi-vendor device integration, hierarchical system designs with submasters, scalable expansion without protocol redesign, long-term maintainability across technology generations. By formalizing how utility devices represent, transmit, and interpret operational data, DNP3 establishes a common technical language for utility automation systems.